All right, hello everybody. Let's keep this on top. I'm hearing myself, which I do not want. Hmm, But I also don't want to mute the mic. Yeah, that probably muted the mic. All right, so what we're going to do today is, I don't like this at all. So I hope I just turned down the volume for myself there. Okay. Let me know in the chat if that somehow turned down the volume for you as well. Um, let's see. Today I'm going to solve an exercise that I have not solved before. It's called Secret Handshake, and it has been published very recently, which is the reason I haven't done it. And this is going to be all about bits and bytes and bitwise operations. Yeah, hope it's going to be interesting. So let's read through this. You are starting a secret coding club with some friends and friends of friends. Not everyone knows each other, so you and your friends have decided to create a secret handshake that you can use to recognize that someone is a member. You don't want anyone who isn't in the know to be able to crack the code. You've designed the code so that one person says a number between 1 and 31, and the other person turns it into a series of actions. Now, your task is to convert a number between 1 and 31 to a sequence of actions in the secret handshake. The sequence of actions is chosen by looking at the rightmost 5 digits of the number once it's been converted to binary. Start at the rightmost digit and move left. Okay. The actions for each number place are wink, double blink, close your eye, jump, and this one's special, I suppose. The leftmost bit says to reverse the order of operations in the secret handshake. Start with the rightmost digit and move left. I don't think we can do that. Let's use the number 9 as an example. 9 in binary is 1001. The digit that is farthest to the right is 1, so the first action is wink. Going left, the next digit is 0, so there is no double blink. No, so we leave our eyes open, and the fourth bit right here is 1, so we jump. That's going to be this one. Okay. That was the last digit, so the final code is wink, jump. Yeah, so this bit and this bit is set, so we do that. Given the number 26, which is 11010 in binary, we get the following action: double blink, jump, and then reverse actions. The secret handshake for 26 is therefore jump, double blink. All right. And it's referring us to, oh, this markdown link looks a little broken. Maybe we're gonna post that in a forum or something later. All right. We don't need to look up what binary is, but we need to grab the exercise. So we got the command right there. Let's jump over to our editor. There we go. And I probably want to make this a little bigger. Just 1 second. All right. So we got some new stuff in there. And that'll be Rust, secret handshake. We'll open the lib, and also we're going to have to unignore the tests later. So let's open them now. Okay, I do want to make this a little bigger. That's a little very big, but you know what? I like it. Um, I suppose this should be comfortable for everyone watching to see. Maybe it's a little too big. No, this is fine. Those are the tests, and what do we do here? What are we doing? So we only have one function to implement. Actions, we're getting it as a byte. That is enough size for 5 bits. And what we need to return is a vector of static strings. Okay, so let's actually start by just declaring these static strings that we're going to have to return. Um, let's jump back into the browser. And these are going to be our strings right there. So let's paste them here and make the syntax valid. So that's going to be static. Let's just put the name later. Oh, and we also need a type annotation. Static and const variables always need type annotations in Rust. So let's call this wink, and this we're going to call double link, and then we're going to call this close eyes, and the last one is going to be jump. All right. Now, how are we going to iterate over these bits? I think the simplest way to do that would be to iterate over, like, I guess, the index or the offset, however you'd like to call that. Um, Starting at the rightmost bit is going to be easy. That means starting at the 0 offset. So if we are just iterating, we're going to start at 0, and we want to stop at, um, let's see, we don't want to look at the 5th bit in this loop because the 5th bit is special. So we're just going to iterate over 4 bits in this loop. And then let's maybe put down a little mark here so we don't forget, right, to handle the 5th bit. Let's see. How can we find out if the bit at the offset I, well, let's call that offset. I is, you know, it's traditional but not very descriptive. Um, Bit offset, something like that. And how are we going to do that? What we're going to need to use are bitwise operations. Let's see, let's just call this x for now. We can improve that later. If we take n and we use the bitwise AND operation with a single bit left shifted by the bit offset, that should give us so this is masking out the bit that we need. So I'm wondering how maybe I should spend a little time to illustrate that. So this 1 is just a bit, right? And what the left shift operation does is move that bit in the pattern. So let's say let's say this is a byte always has exactly 8 bits. So this 1 is just a 1 in binary right here. And if we're going to left shift this, let's say by 1, this is going to equal this number right here. So you see that the bit right here is shifted to the left by one position. And equally, if we do that twice, the 1 is going to end up here. Great. And let's quickly talk about the bitwise AND operation here. So if we have this is comparing two bit patterns, and it's going to keep the bits which are present in both patterns. So I guess the simplest way to illustrate that would be just maybe have something like this. And let's put it on top of one another so it's easier to see, right? If we look at, whoopsie, yeah, let's finish this. The AND operation of these two things is going to be, let's see, yeah, we put the 1 right here. Okay, so this is going to be the result. And what's happening is that it's comparing all of the bits, and if both bits are 0 at the same position, the resulting bit is also going to be 0. If just one of them is 1, either the top or the bottom one, then it's also going to be 0, the results. Only if both bits in both patterns are 1, the resulting bit is also going to be 1. So with this, what this is creating is usually referred to as a mask. And with that mask, it allows us to extract that one bit we want to look at. But this is not perfect because, let's say for the wink, this operation would result in a 1 or a 0. But for double blink, which is left shifted by 1, this operation would result in a 2, right? So the double blink would be something like that, right? And if this operation here is going to give us the bit at different locations every time, then we still need to figure out a way to like compare them universally. And for that, we're just going to compare them to 0, right? So the wink would be the binary number 1, double blink is binary number 2, close eyes binary number 8, and jump is 16. And to check if this operation here did return a bit or did not return a bit, we can just compare it to 0. So let's try to give this a name. A little bit of a better name is bitset. No, maybe something like that. And now I guess we are going to need the indexes, the bit offsets, to use those static strings as well. So let's say if the bit is set, we want to put the string into our vector. So we also need to create a vector. Let's get rid of this because it's getting kind of crowded. And let's just start with an empty vector. And I guess we're only going to need 4 elements, so that's fine. And if the bit is set, we are going to put these strings in the vector. But now we need a way to index, because the only information we have is this bit offset. And what we can do is, I think it was called operations, right? So let's just do a static slice of string slices, and we can just put these right here. Something like that. Okay, that looks all right. So now we can index them. This is at index 0, exactly what we want, index 1 and 2. And in this case, we could say res.push operations and the bit offset. Yeah, so Clippy is telling me it doesn't like the code that I wrote. Clippy is kind of opinionated and doesn't want you to do too much index operations, I guess, but in this case, we actually need it. So the thing that Clippy is going, yeah, Clippy doesn't like this. Clippy doesn't want you to iterate over the index and then index into some slice or array, because almost all of the time, the nicer thing to do is to iterate over the elements directly. So, but that would give us the operation itself, right? So we don't have the bit offset, the index anymore, but now I guess we have the string itself. If I take this away, am I going to get no? So let's just iter copy, because I don't want to have a double reference. Okay, just a single reference now. But we still need that bit offset. We don't need it here anymore to index, so we can just use this operation directly. But we still need it here. And what you can do in Rust is enumerate the items of an iterator. And what that's going to produce is going to take each element, add or put it together with the index into a tuple, right? So the index is on the left side of the tuple and the operation is on the right side. So now we have access to both the offset and the operation itself, and Clippy is happy because we're not doing indexing over here. Indexing is kind of error prone because, if you have off by one errors, then your program is basically going to crash at runtime, and probably you don't want that. So it's a good lint, maybe a bit overkill for this exercise, but let's keep Clippy happy. All right, so I think we got all of the operations that we need inside of the vector, and what remains to be done is reverse if the fifth if the fifth bit is set. So we're just going to do something similar here. We're just going to use the offset 4 at this offset. Yeah, and we also need to compare it to 0, obviously. So this is the offset where the reversal operation would be. And if that bit is set, we're just going to, well, the standard library of Rust is helping us out here, and we're just going to reverse the vector. And I think maybe that might be it. Let's try to go in there, and that would be secret handshake. And probably only one test is, yeah. What is happening? I guess I didn't do something correctly. Thread wink for 1, panic that assertion failed. Wink. Oh yeah, it looks like we're doing it the wrong way around, right? So it's expecting a wink in the output, and we are returning exactly the opposite of that. So I suppose the comparison to 0 should be, yeah, unequal to 0. Let's see, so that's passing for now. And let's unignore the rest of the tests. And we're done. That's very good. Um, let's commit that for now. And let's see if we can refactor this a little bit. Um, I guess we don't need all of these static strings right here. Um, maybe we can clean this up a little bit by just putting them right in the slice. I think I like that better. Yeah. And maybe we can also try to... yeah. So I'm thinking, could we use an iterators for this and get rid of the for loops? But especially this right here, the special bit at offset 4 is going to make that difficult for us. There are iterators which can be reversed, but not all of them. Um, let's see. What would be nice if we could create an iterator over up to 4 string slices, and at the very end, maybe reverse it or not reverse it, I guess. But I think for a couple of reasons that would be complicated to do, and also it might not work for the iterator we do create, because there is a method reverse on iterators. So iterators can be reversed. However, it requires the trait double-ended iterator. And I don't think we're going to read through the entirety of this, but essentially, iterators over data structures which can be iterated over from front to back or back to front usually implement this trait as well. So one example of that would be a vector. Um, if we jump back, nope, that was wrong. Yeah, let's jump into the editor. Let's do a little pseudocode here. Yeah, I think ranges. Ranges is a good example, right? So if you want to iterate over a range like this, and let's just use the I for now to get rid of the warning. Now we have a range here, and what if we want to iterate from let's say 5 to 0, right? We're gonna get an error here, and oh, this is fantastic. I don't even have to do anything, right? It's telling us exactly what to do. It's telling us to write the range from the low to the high number and then reverse the range. And that is exactly the method that we saw in the standard library documentation. And I can type for some reason. There we go. And we need to wrap that in parentheses, and here we can call reverse. The reason we can call reverse is because, well, ranges implement this double-ended iterator trait. Maybe we can even figure out which ones do and which ones don't. So we have the trait double-ended iterator, and if you're looking at a trait in the Rust documentation, if you don't know, if you publish a crate to crates.io, your own crate, documentation will be generated automatically by Rust format, and this documentation is standardized, so this information applies to all third-party crates and crates that you publish yourself. If you look at a trait, in the sidebar, you're going to have a section about the implementers, and here we can see all the types in the standard library which implement this trait. Let's see if we can find ranges. There we go. That's not exactly what I was going for. This is range over B-tree map, which I guess is also a range. But I guess there are a lot of implementers here. Maybe we can search for range. This is still B-tree. What is this? I don't know what this is. Range mut. Oh yeah, so this is also something with B-tree maps. That's it. B-tree set range, stodops range. There we go. That's the one we're looking for. So in this list of implementers, you can check which of the types in the standard library implement this. Why am I talking about this? Maybe we can try to, I think we're going to fail. Let's just try, and it'll be instructive why we fail. Here we have an iterator. Let's put that like this. This is an iterator over the tuples, and what we're doing here is we're basically, yeah, this is a filter map, right? So what we're doing is we're filtering. If a certain condition is met, then we want to keep the element, the item in the iterator, and if the condition is not met, we throw it away. That's basically what we're doing. So let's write a filter, and the condition is purely based on the index, on the bit offset here. So we only need to look at the first element in the tuple. The second element we can ignore with an underscore, and the condition is simply going to be this. This is the condition to keep an item. Great. And next we're going to need to map this, because right now we still have the tuple of both the index and the string slice, and we want to throw away the index, the bit offset. This is the operation, right? We want to keep the operation. Great. So now what this is, if we look, yeah, the type annotation is a little bit gnarly here. So these are just deeply nested generics of all of the iterators, adapters that we've used. The important thing about this is that it's just an iterator over string slices. Can we somehow make Rust Analyzer tell us that? I don't think so. I think we could, yeah, let's not do that. So this is just an iterator of this string slices. And then what we can do is collect this into, let's say, a vector. Something like this. Okay. And if we do that, now it's telling us, yeah, it's collecting the items of the iterator into a vector of string slices. And this works fine for these elements, for these four elements, the operations. But now we kind of want to reverse it, and I'm not sure we can. We can. That is fantastic. Okay, but we're not over. We're not quite. We haven't quite succeeded yet. This is very cool. Okay, this is super cool. Operations is a slice, and we're iterating over the slice. And iterators over slices implement the double-ended iterator interface trait, meaning that this obviously can be reversed. This is not a surprise to me. What kind of is a surprise to me, well, it's just very cool, is that all of these iterator adapters that we're using, the information about the underlying iterator, the fact that it can be reversed, is preserved across all of these iterator adapters, and we can reverse at the very end. So that's pretty cool, but we don't always want to reverse. Sometimes we only want to reverse based on a condition. And what we can do is, this might get interesting. Okay, this is probably going to be interesting. Yeah, let's see. Let's store this thing, right? This is an iterator. The type is kind of ugly looking. Actually, that's not the entirety of the type. So that the full type doesn't even fit on a line. Let's just call this iter for now. This is our iterator, and now we need to decide based on this condition, do we want to reverse it or not? So what we could try, it's not going to work, is we could try to mutate this iterator and say, okay, if this condition is met, we reassign the iterator to itself, but reversed. That technically works, right? But the type system is getting in our way, namely because this obviously returns, it doesn't return the same type. So the input, this iter, is the input type, the type self, but the output is not the same type. It's the input type wrapped in this reverse type. And that's why the compiler is yelling at us. We cannot assign a different iterator, a different type to this variable. So let's think about what we can do here. I mean, there is an easy way out. Let's quickly do the easy way out, and after we've done the easy way, we're gonna make it a little harder on ourselves. Um, what we can just do is we can just say if the condition is met, um, we reverse and collect, and if it's not met, then we just collect, and that's just going to be our return value. Let's see. Let's see if that's right. Why is this working? The fact that these two types are different, it's just in different branches, and the collecting at the end collects both of these iterators of different types are both going to be collected into a vector, so the types match again, and we have the correct return type. Let's see if that still is correct, and it is. So let's commit that real quick. Let's challenge ourselves even further, because every once in a while you will get into a situation like this, and this is always the easy way out, to just return a vector. But Rust is a systems programming language, and we want to be able to go fast. And the problem with this is that vectors are heap allocated, and maybe what you sometimes want to do is, let's write this action function here again. Let's copy this. What you sometimes want to do is, right, how do I explain this? Actions iter, let's call it like that. So a common situation is that, let's say this function here is called, right? And it's called with some number. And what happens next is we're just going to iterate over this vector right um, afterwards. Why is this a problem? Whatever, let's just print this. Okay, that's cool. I don't want this warning, so leave me alone. Okay, let's look at why this is a problem. What we're doing here is we're collecting into a vector, which is causing a heap allocation. And this might be in this case, it's not a very big heap allocation, right? It's just going to be four pointers. So it's a very small heap allocation. But imagine you have an iterator over a large number of items. By returning a vector directly, what's going to happen is that all of these items will need to be heap allocated at once in the vector. And if your user does nothing else with this vector, right? This is a vector. If the user doesn't do anything else, then iterate over it, right again, then this heap allocation is kind of useless. And we just lost a little bit of memory efficiency for no good reason. And we are losing like a really big advantage of these iterators, which is the fact that they're lazy, right? The items of all of these operations are only going to be performed once the items are actually being used. And if you imagine you have a program with a couple of pipelines like these, and at every intermediary step of the pipeline, you're doing a heap allocation because it's easier to return a vector, you're going to lose, depending on the situation, a lot of performance. So what do we want to do instead? What we want to do is we want to return some iterator, all right? This may be new syntax to you. What we're saying here is this is not a concrete type, but we're saying we're returning any type that is an iterator over static strings. And if you look down here, yeah, so Rust Analyzer is correctly picking up on that and saying, okay, this vector, it's not actually a vector anymore. This is just some iterator. So we can rename that, right? And looping over that works just as well. So instead of turning the vector into an iterator, it's just taking this iterator directly. This would be more performant, but if we want to do something like this, we're going to run into problems. So we obviously don't need to collect anymore because that's causing a heap allocation. And here's the problem. These two have different types. Now, both of these values are technically iterators over items of type string slice. And just because we write this syntax doesn't mean we can return different types at runtime. The compiler still has to be able to figure out what is the actual concrete type, and there can only be one that we're returning at compile time. And there is one solution to this, and we're going to do that next. And it's still going to cause a heap allocation. And what we're going to do is instead of statically using static generics, which the compiler requires to be able to figure out one specific type, we can make this dynamic, right? How how are we going to do this? We have to box it. Let's do the box. That's going to be an interesting error message. Instead of impl, right, this impl is a keyword to say, hey, compiler, figure out the actual type for me. But there is another keyword, and that is din, meaning that do I want to talk about what that compiles to? This the din keyword means that we can use generics at runtime. This is a runtime polymorphism. With most object-oriented languages, you get this for free, or almost, I mean, all objects at runtime support this by default, which in those languages means by default every object has this little bit of overhead. In Rust, you have to declare it specifically. It means that basically the actual object that we're returning has to be behind a pointer. We're going to talk about what kind of pointer we can use for this. It has to be behind a pointer, and Rust is going to store type information about this object alongside the pointer. And type information is basically going to be a vtable, so a table of functions, and which can be called on this object. In the case of iterator, the most important function will be next. So what we would be returning here is a pointer to the iterator itself, as well as some additional information about where this function next can be called. Now, the reason we're getting errors here is because we're not telling the compiler what kind of pointer we're using for the indirection that we need. One option is to use a reference, but when you return references in Rust, you always have to specify the lifetime. And we could say that the lifetime is static, but the lifetimes of these iterators is not static. What we're going to do is we're going to heap allocate it. So we are going to put this iterator inside a box. And we're also going to put both of these in a box. Let's see. Closure may outlive the current. Ooh, okay. So this is also an interesting and probably a little difficult error message if you come across this for the first time. Closure may outlive the current function, but it borrows n, which is owned by the current function. Okay, so this is about the borrow checker, and what's happening here is that n is a value, it's owned by the current function, and it's going to be dropped at the end of this function. Now in the case of n, this is a byte, so it doesn't really matter, but just imagine the n is like some large heap allocated object. If it is dropped at the end of the function, that means it's going to be deallocated, right? Yeah, of course, it's not happy about that. Let's say we drop n somewhere. If n was heap allocated, this dropping would cause a n to be deallocated. However, the filter method on the iterator adapters is lazy, meaning it is only executed once the item of the iterator is actually requested. And because we are returning the iterator directly, this may be at a later point in the program. So specifically here, this is the point in the print line, or I guess here in the for loop is where we're actually requesting the item. And this is going to be the point where the filter function with this closure is actually going to be called. Now that means that if n was heap allocated and it was dropped here, or it was dropped at the end of the function, this closure would not have access to this n anymore, right? Imagine if Rust was not memory safe, like C or C++, um, you could do this, and I'm not sure, maybe the compiler would warn about it. I've heard that C++ compilers are very good at warning these days about stuff like that, but in Rust, this is a hard compile error. This would be a dangling pointer, right? So this n would refer to a place in memory that has been deallocated, and there may be other stuff there, there may not. So this would be a very bad bug. How do we fix this? Because n is not heap allocated, it's just a byte. So can't we just keep around a copy of this byte in here? And yes, we can, if you specify the move keyword in front of a closure. This closure is going to take ownership of all the values that are being used inside of its body. Um, yeah, okay. Leaves the original intact. So this is actually just Clippy, the linter. This is not a compiler error. This is totally useless. Don't do this. Okay, this is useless because it's a byte. And what this does is, instead of like taking a reference, borrowing this n, it's moving it into the closure. And because n is a byte, it actually is just copied. So this move keyword fixes our problem here. Just remove it again to see the error message. Closure may outlive the current function, but it borrows n, which is owned by the current function. And it actually tells us what to do. So again, if you're having problems with Rust, do be sure to read the error message carefully. To force the closure to take ownership of n and any other referenced variables, use the move keyword. It's telling us exactly what to do, and it's actually giving us a quick fix. So I could have just quick fixed this, but I hope the explanation was interesting. So this should be working now. Let's try to rewrite our actual exported actions function in terms of our new function. So we're putting this in there, and of course at the end we have to collect into a vector. Let's see if we made any mistakes. And this is still working. Okay. So let's commit that. That's version 3, I guess. And you might be wondering, we're still doing a heap allocation here, right? And you would be correct. This is a heap allocation. However, and in this situation, it's not an improvement at all, because the actual vector that we're producing here is very small. It's just got 4 elements, 4 pointers, so it's not a big heap allocation. But if you imagine this is an iterator over a large number of large structs, then collecting into a vector, that would be a very large vector and a large heap allocation. However, this box right here, it's only storing a pointer to the iterator with some additional information, the virtual table, the virtual function table, which basically, yeah, adding the information at runtime about what the exact type of this iterator is. So if you have a lot of large elements in these iterators, putting them in a box with a trait object, I think the correct term for the syntax right here is these are going to be trait objects. This can reduce the size of heap allocations that you need. Now, we may think about can we get rid of that as well, but honestly, I don't think so. What we could do, I don't think that's going to work. I'm not sure. Yeah, I don't know. If you have an idea, feel free to drop it in the chat, but I think this is as good as we're going to get. Um, Again, for this specific case with these small iterators, it doesn't matter to do this, but it may be an optimization worth for certain use cases. I think that's all I have to say about this exercise, and we are almost 1 hour in, so I'd say that's it for today. Next week is going to be my last stream for Mechanical March, so feel free to say hi, and have a good night.